kind of mirror do you see up on the board here right now? There's two names for it. I don't care which name you give me. What's one of them? Good. We call it a concave mirror because it's caved in the middle. It's thinner in the middle than it is at the edges. What's another name for that concave mirror that Parker just gave me? Yep. It's converging. We call it a concave because it's caved in the middle. We call it converging because rays that are parallel to the principal axis, this is the principal axis, by the way, rays that are parallel to the principal axis will all converge at that point. They'll all come together at that point. It doesn't matter how far away the rays are from the principal axis, as long as they're parallel to the principal axis, they're going to converge at that one point. What do you call that one point? This one point right here where the rays converge. It's called the focal point, yeah. What's this point out here? What's the significance of that? Yep. Yeah, if you do a complete circle here, like let's say this lens is a soccer ball, and the inside of the soccer ball is really, really shiny and reflective. If you measure the radius of that soccer ball, or right smack to the middle of that soccer ball, that's going to be the point that we're talking about right there, the center of curvature, the radius of it. Now, how does that relate to the focal length there, the distance from the mirror to the focal point? The distance from the center of the soccer ball or the center of the mirror to the focal point, sorry, to the mirror itself, is twice the distance of the focal point to the mirror. And that's going to be the case every time. So if you ever see a situation where you're given a number for the center, the radius of this mirror, then make sure you just cut it in half, and that gives you the focal length of the mirror, the distance from the mirror to the focal point. We can call this C. We could call it R if we wanted. We could even call it 2F if we wanted, because it's twice the focal length distance. All right. We're going to draw, yesterday we drew 10 ray diagrams. Today we're going to draw 4 ray diagrams. Same diagrams, just repetition, right? Just review of what we did yesterday. We're going to draw 4, though, of different situations, just as examples, to show us what happens when the object is placed in different spots, what kind of image we get, what attributes or characteristics we get when we place that image at that object at different spots. First object we're going to place way out here. It's beyond the center of curvature. This is the inside of the soccer ball. It's almost over on the other side of the soccer ball, okay, the other wall of the soccer ball. First ray we're going to draw is reflecting off of the top of this object. Where does it go when it hits the mirror? Where does it go when it hits the mirror, Matt? Yeah, it goes down through the focal point. We just did that, right? All rays parallel to the principal axis go through the focal point. So this one goes through the focal point. Listen, there's millions of rays that are reflecting off of this object. We're picking 2 of them. We're picking this one because we know what happens to it. We're picking the next one because we know what happens to it. The other million rays that reflect off of it, we could, using the law of reflection, figure out what happens to those as well. But these ones are just so predictable that these are what we're picking here. Second ray, from the top of the object down through the focal point. Where does it go? It's the symmetry of physics, right, Parker? Where does it go? Parallel to the principal axis. If parallel goes through the focal point, then through the focal point is also going to go parallel to the principal axis. Now, the bottom of the object is right here at the principal axis. The bottom of the image is as well. The top of the object is right here where the lines start. The top of the image is right here where the lines finish. So our image is going to be formed right there. There's 3 characteristics of this image that we can express, or 3 attributes of this image that we can express. Gary, what's one of them? It's smaller. We usually express these characteristics in a particular order, and Garrett gave me the first one that I usually give. Smaller, larger, same size. It doesn't matter if you give them to me in that order or not, though. Cole, what's another one? It's inverted. It's upside down. It's flipped over, however you want to say that. And what's the third characteristic? This is the hardest one, although I think by now we're starting to get this. Colin? It's real. Now, how do you know that it's real? Yeah, you can project it onto a screen. That's what defines a real image. It can be projected onto a screen. But how do you know in this diagram, Javi, that it could be projected onto a screen? Good. When solid lines intersect, it can be projected onto a screen. It's a real image. Good. Let's take a look at another one now. Let's say our object this time is in between F and 2F, or in between F and the center of curvature. First ray, same deal. Parallel, where does it go? Josh, where does it go? Down through the focal point, good. Second ray goes down through the focal point. Tara, where does that one go? Good, parallel to the principal axis. Okay. Now, the object starts at the principal axis, so does the image. The object ends where the rays start. The image ends where the rays converge. That's going to be our image now. Andy, what's one of the characteristics here? And doesn't matter what order you give them to me. So if you think of a one, just give it to me. Larger, smaller, same size, up, right. It's a real image, yeah. Okay, so he gave me the one that we usually give third. That's okay. It's a real image, which means that it can be projected onto a screen. We know that because it's solid lines that are intersecting here. What's one of the other ones? Mason, what's one of the other characteristics? Good. It's larger, bigger, however you want to say it. And third characteristic, John? It's inverted. It's flipped over. It's upside down, however you want to say that. Good. One more for this type of mirror. This time we're going to put our object way in here, really, really close to the lens. So, sorry, the mirror. So if this is the inside of a soccer ball, the object is almost right up against the wall of the soccer ball. Okay? First ray, parallel to the principal axis, down through the focal point. Second ray, we can't put it through the focal point this time. So we have to actually go to our third ray. Where's our third ray go? Remember that one? We don't see this one as often. Where does the third ray go, Parker? Yeah, it's as if it's going away from the center of curvature, and then when it hits the mirror, it bounces back and goes right through the center of curvature. Those two rays don't intersect. If they don't intersect, we've got to extend them back, extend the reflected portion of them back like this. Okay, when we do that, we see that they do intersect behind here, behind the mirror. Look into the mirror, you'll see the image. It's just going to be behind the mirror on the other side, that's all. What's one of the characteristics there? Joey, what's one of them? It's larger. Kirsten, what's another one? It's upright, right side up. And what's the third characteristic there, Shaden? It's virtual, and you know that because it's dotted lines that intersect, and of course, ultimately, that means that you could not project that onto a screen even if you tried, right? One more ray diagram, but for the other type of mirror this time. What kind of mirror is this? What's one of the names, Kevin, for this mirror? Convex. Yeah, it's bulged out in the middle, thicker in the middle than it is at the edges. What's the other name for the convex mirror, Ryan? Convex or diverging, yes. Converging, the rays came together. Diverging, the rays spread apart. So if I've got rays parallel to the principal axis here, they're going to go away from the focal point. Right? Diverging mirror. We're going to draw an object. Doesn't really matter where we draw it. Let's draw it out here. The reason it doesn't matter is because all 5 of these possibilities are going to give me the same characteristics of the image. The ray diagrams all look the same. First ray, parallel to the principal axis. Where does it go? Well, we just said. It goes away from the focal point like this. Second ray goes down toward the focal point, but it can't go all the way to the focal point. How come? It gets reflected first. It hits the mirror and gets reflected. Where does it get reflected, Colin? Parallel to the principal axis, right? Parallel away from the focal point. Well, I'll go toward the focal point. It's going to reflect parallel. Let's extend these because they don't intersect on the left side. Extend them back like this. Okay, this one goes back there. This one goes back parallel to the principal axis. They're going to intersect here, which means the characteristics or the attributes of this one are what, Mark? Give me one. Smaller. Queen, you weren't here yesterday, were you? Kyle, we're going to call on you for this then. What's the next one? Upright, right side up. And finally, the third one is, Jeff, you weren't here yesterday either, were you? Kate. It's virtual. How do you know it's virtual? I'm sorry? Good. Solid lines don't cross, which means dotted lines do cross. Okay, ultimately, that means that we could not project it onto a screen. Okay, we've seen these mirrors a million times. Okay, we talked about this yesterday. At the rec center, okay, in the corner of the hot tub. Okay, you see it on the passenger side of a vehicle, sometimes even on the driver's side, especially with With semi-truck drivers, they tend to put those little circular mirrors in the corner of the mirrors, convex, so they can see a wider area. Smaller, objects in mirror are closer than they appear, okay, but it at least allows you to see a wider area. Somebody said yesterday, parking garages. I think that was this class. You see them in parking garages. You see them a lot in parking garages, actually, so you can see around corners, right? Good. Well, let's take a look at some mathematics here today. We know how to draw the ray diagrams. We know how to find attributes or characteristics of the images. We know even how to find where an image is going to be located. But let's do it mathematically now instead of graphically. There's good news and bad news. Here's the good news. There is only two equations. 1 over f is equal to 1 over dO plus 1 over di. And the other one is m is equal to hi over ho equals negative di over do. I kind of cheated a little bit. I said there's only two equations. Really, there's, okay, this one's like two equations in one, so really there's three equations, but we write it as two. Let's identify what some of these things mean. F stands for the focal length. The focal length is the distance from the mirror to the focal point. Simple as that. DO is my object distance. It's the distance from the mirror to the object. And DI is my image distance. It's the distance from the image to the surface of the mirror. Easy enough, right? We've already identified these. HI is the image height, how tall the image is. HO is the object height, how tall the object is. And finally, M, which we're going to circle in a different color, and you'll see why in a minute. M stands for the magnification. The magnification is how high the image is relative to the object. So in other words, if you have a magnification of 5, then that means the image is 5 times bigger than the object. If you have a magnification, who takes biology here? Who does biology? Who has taken biology? Okay, you've used the microscopes in biology, right? Where the magnification might be 40x or 400x. If it's 40x, it means that the image is 40 times the size of the object. If it's 400x, then the image is 400 times the size of the object. Now, what about units? What about the units there? What unit do you think we'd use for focal length, image distance, object distance? Meters. Meters is the standard unit, right? But if you notice, because these variables, although they're not the same variables, they have the same units, appear in every term, F, DO, and DI, the units would actually cancel here. So if you want to use centimeters or even inches or miles, something other than meters, you can get away with that here. Okay. Usually we don't focus on that because it's probably better almost always to go back to standard units. In these equations, it's often convenient to use centimeters. Okay, we almost always see centimeters as our distances. And if we don't want to convert those, we don't actually have to convert them here. So I'm going to write down that image distance, object distance, focal length, all of these distances, centimeters, meters, feet, etc. Anything that represents distance, as long as we're being consistent through the problem. You can't switch units midway through the problem or midway through an equation. Now, the reason that I've put magnification in a different color is because the units for magnification are different. Take a look at one or more of the equations and tell me what units we'd use for magnification. Good, Ryan. There are no units associated with magnification, and that's because they cancel, right? Centimeters over centimeters, or meters over meters, or feet over feet. It doesn't matter. The units end up canceling out. There are no units. Now, sometimes you might put an x beside the number, 40x, 400x, 3x. 0.5x, whatever the case may be. But you don't have to. Okay, if you just put a 5 or a 40 or a 400, that's good enough. If you see an x, that's what it means, but it's not necessary. All right, that's the good news. Two relatively simple equations here. That's all we're ever going to use for these problems. Here's the bad news. They all have signs. They all have positives and negatives associated with them, and we have to be able to identify when they're positive and when they're negative. It reminds me a little bit of remembering 21 different frequency, wavelength, and energy ranges for the 7 types of EMR. Okay, there's a big table here that we got to remember. The good news is, once again, just like with the 7 types of EMR, frequency, wavelength, and energy, there's a way that allows us to make it a little bit quicker, make this a little bit quicker to remember. There's patterns that end up forming. Let's identify, first of all, 3 variables, F, DO, and DI. And let's identify when those 3 variables are positive and negative. We'll group them together because the pattern you're going to see, is the pattern that's formed when we identify those 3 variables, F, DO, and DI. F is going to be a positive number whenever we have a real focal point. And it's going to be a negative number whenever we have a virtual focal point. What does that mean? A real focal point, a virtual focal point. Let me go back to my ray diagrams. Diagram 1, diagram 2. Tell me which one you think has a real focal point. Diagram 1 or diagram 2? Josh? Why 1? You're right, by the way. Why 1? That's the one that's outside. What do you mean outside? Okay, good. So that's where rays actually go through. You have rays really going through the focal point. Not all the rays do. Rays parallel to the principal axis really go through the focal point. We're going to make it a real focal point. Rays parallel to the principal axis don't really go through the focal point there. They diverge away from the focal point. They virtually go through the focal point. So we're going to make F positive when it's real, when we have a converging mirror. And we're going to make it negative when it's virtual, when it's a diverging mirror. DO, you're going to start seeing a pattern in a second here. DO is going to be positive when it's a real object. And it's going to be negative when it's a virtual object. Here's the good news, as far as this one goes. For you guys in Physics 30, the object will always be real. Now, it doesn't have to be later on in physics for you. If you have a system of mirrors, 2 or 3 or 4 mirrors in the system, and light's reflecting off of one of them, forming an image, and that image becomes an object for another one, and that image becomes an object for another one, and so on, it is possible to have a virtual object, or even more than one virtual object. But for us, we won't see that. Okay, we won't see a virtual object. So for us, we're always going to make DO positive. We're never going to make DO negative. If you take a course in physics in university, okay, that might not be the case, depending upon how deep they go into it. You may see a negative DI. Okay, but for grade 12, as long as we're here until June 25th when we write the diploma exam, DO will always be positive for us. DI? Well, it's going to be positive when you have a real image. And sometimes it's real, sometimes it's virtual, so there's no hard and fast, always this, always that for DI. It's going to be negative when you have a virtual image. See the pattern here? F, DO, DI, everything in that first equation is positive if it is real. It's negative if it is virtual. Let's identify two more variables now. Let's identify HO and HI. They can also both be positive and negative, except that it's not because of whether it's real or virtual. HO and HI, positive, negative, is based on whether it's right side up or upside down. So HO is going to be positive if it's an upright object. And it's going to be negative if it's an inverted object. HI is going to be positive if it's an upright image. And it's going to be negative if it's an inverted image. First three are based on whether it's real or virtual, and the last two are based on whether it's right side up or upside down. Good? We're missing one. What variable are we missing here in this table? Which one is it? M, magnification. The reason we haven't put it in the table is because it doesn't quite fit. It almost does, but not quite. M, the magnification, is positive, not when the object or image is real, not when the object or image is right side up. M is positive when the object and image are both on the same side of the principal axis. What does that mean? What does that mean? Well, if the object is right side up and the image is right side up, they're both on the same side of the principal axis and M will be positive. If the object is upside down and the image is upside down, HO and HI are both negative, but M will be positive. So if they're both right side up, they're both upside down, M will be positive if they're on the same side of the principal axis. Sometimes they call it the attitude. Right side up, upside down, the attitude. If the attitude is the same, then we're going to say that M is positive. If the attitude is different, in other words, one's right side up, one's upside down, if the attitude is different, then it's going to be a negative magnification. So you get a magnification of +3. It means the image is 3 times bigger than the object, and they're on the same side of the principal axis. You get a magnification of +0.5. The image is half the size of the object, but they're both on the same side of the principal axis. -3 means, well, the image is still bigger than the object, but it's flipped over relative to the object. -0.5, the image is smaller than the object, and it's flipped over relative to the orientation or the attitude of the object. You're going to work on some problems here in just a moment. When you work on these problems, I'm going to ask you to make sure you have this table written down and right beside you. You need to know this table. You're never going to be given a question that says, fill in the table. At least I don't think you will. I'd be very, very surprised. Okay, they don't typically ask questions like that. But you will have to use it. The best way of remembering it so that you can use it properly is not to sit down tonight and try to memorize this table. Okay, it's to use this table. Keep it beside you. Okay, come quiz day, come test day, you're not going to be able to do that. But the good news is you should remember it come quiz day or test day if you have it in front of you as you're doing these problems. So don't try to be, don't say, I'm so smart, I don't need to have the table beside me. I'll just remember it for the questions I do today. Don't do that. Have it beside you. Use it as you're doing the questions today. Okay, and then be so smart tomorrow after you've used it a bunch of times. Because I want you to do that, I'm going to copy over that table and paste it into the example problem that we're going to work on here. Keep it beside you. Refer back to it. Don't try to be a hero and memorize this table right away. Question 13.2 on 664 says an object located 20 centimeters from a converging mirror has a focal length of 15 centimeters. Going to pick up my red pen. What do you think I want to circle here? What do you think I want to circle there? Andy? Centimeters, although for these questions, it doesn't really matter, right? Centimeters is okay as long as I'm consistent. Okay, but by all means, okay, if you don't spot that right away, but you do spot centimeters and you want to always go back to meters, then by all means, circle that. Draw attention to it. What else did I want to circle there? The converging mirror. That was important to me. How come? How come? Why was that so important? Yep. Very good. Tells you whether F is going to be positive or negative. I would, if I was you, whenever I see what kind of mirror it is, just write down F is positive or F is negative, as the case may be. Now, if you miss it in this one, you get away with it, right? Because if you forget to put a sign in, it's going to be positive by default. But if it was ever a diverging mirror, you're not going to get away with it. You got to make sure you make it negative. We want to find where the image is going to be formed. We got a height here. We want to determine the attitude. The attitude is right side up, upside down, the height, and the magnification. So we got lots of things here. This is going to be DO. This is where the object is. This is going to be F. This is the focal length, and it's positive. We want to find DI, where the image is. Here's HO. We want to find HI. We want to find M, the magnification. And we want to find whether it's right side up or upside down. We'll worry about that later. We only have two equations. Only have two. So let's try one of them. You got F, you got DO. Let's find DI. Let's say 1 over F is equal to 1 over DO plus 1 over DI. Let's plug our numbers in. Don't try to rearrange this first. It gets ugly with the fractions. 1 over 15, and it's positive, is equal to 1 over 20. DO is always positive. Plus 1 over DI. How many of you are getting a little bit scared right now? Because we got some fractions to deal with. Adding fractions. Oh, you guys are good with fractions? Good. Do it the old-fashioned way. Find a common denominator. 4 over 60 minus 3 over 60 gives me whatever, 1 over 60, okay, which is 1 over DI. Flip it over, get the image distance. That's fine. Do it that way. I love it if you can use fractions. But I'm going to give you a little cheat as well. I use that term loosely because you're not really cheating. Take your calculator and do this. 15 x to the minus 1. That's 1 over 15. But you got to take the 1 over 20 over by subtracting. So let's say subtract 20 x to the minus 1. 1 over 15 minus 1 over 20. Gives me, what, 0.1667. That's 1 over DI. We want DI. Take the inverse of that. My answer is 60. Go ahead and use fractions if you want. Perfectly fine. Okay, if you want to do it a little bit quicker, 15 x to the minus 1 minus 20 x to the minus 1, press equals, then go x to the minus 1 of the answer, and this is what we get. Okay, DI is done. What about the height and the magnification? Let's say the other equation, m is equal to hi over ho equals negative di over do. That negative, by the way, is really important. In order to maintain the integrity of the sign conventions, you've got to put a negative in there. Negative di over do. Now, I don't know what hi is. I don't know what m is, so this part of the equation isn't very useful. But I do know what di and do is. Di is 60, so it becomes negative 60. If di had been negative 60, then this would have been negative 60, or positive. Do was 20, so m is going to be negative 3.00. There's my height. Oh, sorry, there's my magnification. Now I'm going to find the height by saying m is equal to hi over ho. Hi is m times ho. It's negative 3 times my object height, which is 5, which is negative 15. There we go. I got di, I've got m, I've got hi. The only thing I haven't found here is the attitude, right side up or upside down. Who can tell me right now whether this is right side up or upside down? Yep. Why do you say that? Good. Image height is negative. Okay, negative 15. Okay, that means it's upside down. Right? We know this, just refer back to our table. Hey, easy, right? HI negative, HI negative. Oh, inverted image. Got it? All right. Questions to go with this, page 664. I'm going to ask you to do questions 1, 2, 3, and 4 and 5. We never see 5 practice problems, hey? This must be important. This is homework. And as I said, if you finish this up early, have a look at the next worksheet, which is also going to be homework for Monday.